determine the appropriate wire size and protection for a parallel bank of 6-phase converters feeding a 250 amps AC chiller unit, we need to follow a series of calculations and considerations based on electrical codes and engineering principles. Here's the step-by-step guide. Firstly, calculate the total load current. This is the sum of the currents drawn by all the converters and the chiller unit. Given that each of the 6 converters has a full load current, or FLC, of 360 amps and the chiller unit draws 250 amps, the calculation is as follows. Total load current equals 6 converters multiplied by 360 amps plus 250 amps, which equals 2460 amps. Secondly, determine the wire size. With the total load current established, use a wire size calculator or consult the National Electrical Code (NEC) tables to determine the appropriate wire size needed to safely carry this current. Several factors must be considered. Voltage, in this case 240 volts. Current, which we calculated to be 2460 amps. Conductor material such as copper. Conduit type like PVC or EMT, electrical metallic tubing. Temperature rating of the conductor, typically 75 degrees Celsius or 90 degrees Celsius. The NEC provides tables, such as those found in Article 310.15, that correlate ampacity, the current carrying capacity of a conductor, with wire size, insulation type, and installation conditions. These tables account for the conductor's ability to dissipate heat without exceeding its temperature rating, which could damage the insulation and pose a safety hazard. Thirdly, calculate the protection rating. The protection rating refers to the size of the overcurrent protection device, such as a circuit breaker or fuse, needed to protect the circuit from overloads and short circuits. This is typically calculated as 125% of the total load current. In this scenario, the protection rating is calculated as 125% multiplied by 2460 amps, which equals 3075 amps. This calculation is based on NEC guidelines, which require overcurrent protection devices to be sized appropriately to protect conductors from overheating and to prevent damage to equipment. Fourthly, select the protection and wire. Based on the calculations, select a circuit breaker or fuse with a protection rating of 3075 amps or higher. Standard breaker sizes may not exactly match this calculated value, so it is acceptable to use the next higher standard size, as permitted by the NEC. Simultaneously, choose a wire size that can safely carry the total load current of 2460 amps without overheating. Consider damping factors for ambient temperature, conduit fill, and other conditions that may affect the conductor's ampacity. Recommended wire and protection wire size. A suitable wire size for this application is 500 kc male THWN or XHHW copper conductors. These conductors have an ampacity rating that exceeds the total load current of 2460 amps, and they are suitable for use in wet or dry locations. Protection. A 3200 amp circuit breaker or fuse is recommended for overcurrent protection. This size is slightly larger than the calculated protection rating of 3075 amps, but it is a standard size that provides adequate protection for the circuit. Additional considerations. It is crucial to use appropriate conduit and fittings to protect the wires from physical damage and environmental factors. Conduit type should be selected based on the installation environment and local electrical codes. It is also advisable to consider using surge protection devices, SPDs, to protect the equipment from power surges and voltage transients. SPD can help prevent damage to sensitive electronic components and improve the reliability of the system. Always check local electrical codes and regulations for additional requirements and restrictions. Local codes may have specific requirements for wire size, conduit type, overcurrent protection, and other aspects of the installation. It is essential to comply with all applicable codes to ensure the safety and legality of the installation. The NEC provides guidelines for sizing conductors and overcurrent protection devices based on the continuous load. According to NEC Section 215.3, feeders supplying continuous loads must have an ampacity not less than 125% of the continuous load. Since the total load current is 2460 amps, the minimum feeder ampacity required is 1.25 multiplied by 2460 amps, which equals 3075 amps. This means the conductors must be sized to carry at least 3075 amps continuously. The NEC also specifies requirements for overcurrent protection devices in Article 240. According to NEC Section 240.4, conductors must be protected against overcurrent in accordance with their ampacities. The overcurrent protection device must be sized to protect the conductors from overheating and to prevent damage to equipment. In this case, the overcurrent protection device must be sized no larger than the ampacity of the conductors. However, NEC Section 240.4 B allows for the use of the next higher standard overcurrent device rating if the conductor ampacity does not correspond to a standard overcurrent device rating. In this scenario, the calculated protection rating is 3075 amps, which does not correspond to a standard overcurrent device rating. Therefore, it is acceptable to use the next higher standard size, which is 3200 amps. The use of parallel conductors is permitted by the NEC under certain conditions. According to NEC Section 310.10, H. Conductor size 1/0 and larger can be run in parallel, provided that they are installed in the same raceway or cable, have the same electrical characteristics, and are adjusted for ampacity directing as necessary. When using parallel conductors, it is important to ensure that each conductor is properly terminated and that the load is evenly distributed among the conductors. The NEC also provides guidelines for directing conductor ampacity in certain situations. According to NEC Section 310.15, B3 conductor ampacity must be derated when there are more than 3 current-carrying conductors in a raceway or cable. The derating factors vary depending on the number of conductors and the insulation type. In this case, if the conductors are installed in a raceway with more than 3 current-carrying conductors, the ampacity must be derated accordingly. The NEC also provides guidelines for selecting the appropriate type of conduit for different applications. According to NEC Chapter 3, there are several types of conduit that are suitable for use in electrical installations, including rigid metal conduit, intermediate metal conduit, electrical metallic tubing, and rigid non-metallic conduit. The type of conduit selected should be based on the environmental conditions and the specific requirements of the installation. For example, rigid metal conduit is suitable for use in wet or corrosive environments, while electrical metallic tubing is suitable for use in dry locations. In addition to the NEC, local electrical codes may have additional requirements for wire size, conduit type, overcurrent protection, and other aspects of the installation. It is essential to comply with all applicable codes to ensure the safety and legality of the installation. Local codes may also require permits and inspections for electrical work. Before starting any electrical work, it is important to obtain the necessary permits and schedule inspections with the local electrical authority. The use of motor starters for the converters and the chiller unit introduces additional considerations for wire sizing and overcurrent protection. Motor starters are used to provide overload protection and to control the starting current of motors. The NEC provides guidelines for sizing motor circuit conductors and overcurrent protection devices in Article 430. According to NEC Section 430.22, motor circuit conductors must have an ampacity not less than 125% of the motor's full load current rating. In this case, the converters are 60 horsepower motors with a full load current of 360 amps. Therefore, the motor circuit conductors for each converter must have an ampacity not less than 1.25 multiplied by 360 amps, which equals 450 amps. The NEC also specifies requirements for motor overload protection in NEC Section 430.32. Motor overload protection is intended to protect the motor from overheating due to excessive current draw. The overload protection device must be sized to trip at a current value that is slightly higher than the motor's full load current rating. In this case, the overload protection device for each converter should be sized to trip at a current value that is slightly higher than 360 amps. The NEC also provides guidelines for motor short circuit and ground fault protection in NEC section 430.52. Motor short circuit and ground fault protection is intended to protect the motor and the electrical system from damage due to short circuit or ground faults. The short circuit and ground fault protection device must be sized to trip quickly in the event of a short circuit or ground fault. In this case, the short circuit and ground fault protection device for each converter should be sized to trip quickly in the event of a short circuit or ground fault. The use of a 7th motor starter for the chiller unit introduces additional considerations for wire sizing and overcurrent protection. The NEC provides guidelines for sizing motor circuit conductors and overcurrent protection devices for air conditioning and refrigeration equipment in Article 440. According to NEC section 440.32, the branch circuit conductors supplying a hermetic refrigerant motor compressor must have an ampacity not less than 125% of the motor compressor's rated load current or branch circuit selection current, whichever is greater. In this case, the chiller unit has a rated load current of 250 amps. Therefore, the branch circuit conductors supplying the chiller unit must have an ampacity not less than 1.25 multiplied by 250 amps, which equals 312.5 amps. The NEC also specifies requirements for overcurrent protection devices for air conditioning and refrigeration equipment in NEC section 440.22. The overcurrent protection device must be sized to protect the conductors from overheating and to prevent damage to equipment. In this case, the overcurrent protection device for the chiller unit should be sized no larger than the ampacity of the conductors. In addition to the NEC and local electrical codes, it is important to consider the manufacturer's recommendations for wire size, conduit type, overcurrent protection, and other aspects of the installation. The manufacturer's recommendations may provide additional guidance on how to properly install and protect the equipment. It is also important to consider the environmental conditions in which the equipment will be installed. The environmental conditions may affect the wire size, conduit type, and other aspects of the installation. For example, if the equipment will be installed in a wet or corrosive environment, it is important to use materials that are resistant to corrosion. In summary, determining the size of protection and wire required for a parallel bank of 6-phase converters feeding a 250 amps AC chiller unit involves several steps. Firstly, calculate the total load current. Secondly, determine the wire size. Thirdly, calculate the protection rating. Fourthly, select the protection and wire. Additional considerations include the use of appropriate conduit and fittings, surge protection devices, and compliance with local electrical codes and regulations. By following these steps and considering all relevant factors, it is possible to ensure the safety and reliability of the electrical installation.